Hello everyone and welcome to Handmade Hero, show where we code a complete game live on stream. We, I believe, are just left with debugging today. We actually did some nice reorganization last weekend and we cleaned up the lighting code so that it was easier, because it'd been gone through so many experiments with us because, lighting, as I've said many times on the series, is probably one of the hardest things you're likely to encounter in real-time rendering. It's like the one thing that we can't really do. Basically, real-time lighting is just always a hack. There's no actual good solution to it. Obviously, folks at NVIDIA and so on are trying pretty hard to get to a real solution because, their job is to improve rendering. That's what they make money on. And so, maybe someday we'll actually get graphics cards that are so incredibly powerful that you can actually do like fairly real lighting computations every frame and it will actually work, with some amount of denoising obviously, but it'll be casting so many rays to do actual real light transport that all of these hacks that we're looking at won't be necessary anymore. But at least for the foreseeable future, even the next 5 years, that's not going to be the case. We just have way too far to go for at least the indirect lighting part. Direct lighting is probably going to be solved because that's a much more bounded number of rays. Indirect lighting, we're pretty far. And so most indirect lighting schemes that you see in games, and certainly the one that we have here, are just based around some hacks you can do to try and take the number of rays you can cast or the amount of lighting work you can actually do and turn it into something that actually produces a visually pleasing and plausible result, even though we all know full well that it's not correct and isn't going to be even close to correct because we simply don't have enough computing power to make it correct in the 60th of a second that we have to do it. So taking a look at where we've come at this point in the series for our lighting, we've got sort of two methods, and I believe we just can switch between them pretty trivially now. If you take a look at the game running, what you can see is that if we run the old system, which we are trying to improve the performance of, you can see that the lighting works relatively well. It's a little bit flickery, but for the most part, it is generating. We have some work we want to probably do on quality and also on interpolation to improve the shaping of the lighting and so on. So there's things that we'll definitely do kind of downwind of the lighting computation. But the thing that we want to do before we go any further on that is we just wanted to try and get the highest possible performance for this level of light transport. And what we did there is we tried to improve the ray tracer. And if we switch to the new one, you will notice that we don't actually get any results. That is because we have not debugged it yet, and there are a lot of problems. So what we want to do today is just take a look at that. I believe this needs to be, looks like we've removed these values. I gotta nerf them out here. We just want to kind of take a look and say, what's wrong with the routine that we've written so far? I can get rid of this. What can we see that's buggy about it? Can we just do the basic amount of work to get it, nominally working and go from there? Because you can see here, if we run it, what we actually see happening, and I know it's a little bit hard to figure out exactly what's going on there, but what we see happening here is that every ray that's cast just gets full moonlight. So our Raycaster is returning the result for every lighting location. It's just returning the result that it already left the sampling volume and it didn't hit anything, right? So no rays are recorded as ever hitting anything ever. So obviously we know that's not true because if this was working, we would see a result sort of at least somewhat similar to the result that we had with the previous ray tracer. And so we know that it's just buggy, right? It's like something's buggy about it. But since we only just finished it and we haven't had a chance to really carefully go through the whole thing, we don't really know what's buggy because there's 3 separate pieces and any one of them or all of them could be buggy, and we have to start paring it down and getting each one working reliably. So we probably want to go through them piece by piece, doing more testing, seeing if there's assertions we can put in, seeing if there's any kind of like actual testing we can do to try and isolate each piece and get it working reliably. And the three pieces are, one, there's the spatial partition, which we use. It's a grid. It's sort of like the voxel, but it's a little bit larger. It's one voxel unit larger around the entire sides of it. So we want to see if we can make that work reliably to partition the things we're casting against into that grid. We don't know if that works currently. It could just be wrong. So, one very obvious way that we could be not hitting anything is if we don't correctly insert the boxes we're trying to collision detect into the grid. We could have a thing where, you never hit anything because the grid keeps telling you there's nothing you can hit. So there's that. The next thing we have is the walk table. The walk table is the thing that tells you which grid squares you sample for any particular array. That could be totally wrong. It could be telling you to sample all erroneous grid squares. And obviously that would cause you to not hit anything. And then finally what we would have is the actual Raycast routine itself. We did some additional work on that, although the core of it still does do testing the same way, meaning it does actually test for arrays using the same algorithm when we do a comparison between the AABB and the ray. The actual structure is different, and the way it loads the data is different, and the way it finalizes is different as well. So all of those things could be wrong. And there's actually part of that spans two pieces. When we build the spatial partition, we also pack the AABBs we're testing against into individual SIMD units that are easy for our code to work with. And so that part is also worth examining, because if we packed them incorrectly, then when we test against them, they will not test correctly, even if the testing code was correct. So again, three moving parts there, and two of the parts actually have a relationship with each other through that packing structure that we have to look at closely as well, because that wasn't, even though the AABB testing hasn't really changed, we're using the same algorithm. The way we're doing the algorithm is different because the data input has been changed. So we have our work cut out for us, certainly. So it's going to take a little while for us to actually make this go. Let's start by looking at the spatial partition and figuring out if there's any way that we could sort of test that, right? And I think there is a pretty simple way that we could do this. Since we know that we can draw debug boxes, we've already done the work. In fact, we even inside the lighting system have a very specific thing called push debug box. It seems like we should be able to do something where we draw a particular spatial cell. So we could, for example, take a particular voxel cell in the world, and we could draw what that voxel cell thinks its AABB contents are, and that would allow us to visually inspect it to see whether or not the contents of the spatial partition appear to line up with what we think they should. And again, the reason that I typically take this sort of approach is that, in fact, we get asked a lot of times, so I'll mention it again. People always ask me, what do you think of unit testing? What I think about unit testing is, well, unit testing is fine for very simple programs that don't do very much interesting. For complex programs like a game, you really can't unit test because the definition of what it means to be correct is very difficult to actually test. If you have an input, and what you want in your output is that you want a grid that contains clipped versions of the input for each grid square. Well, the routine that you write in order to generate that is the same routine you would need to test it, right? There's no way to write a unit test that tests that without doing that, right? There's no other way to do it. So if you write the routine and then someone says unit test to see if that's correct, well, there's no definition for the output other than run that same algorithm, run that, right? Now, sometimes you can still do this if there's, for example, if your performance, like for our Raycaster, that's something that we could unit test and maybe should in the future, because it's easier to write a crappy, slow Raycaster than it is to write a really highly optimized SIMD one. So we could use a brute force Raycaster to test the total result of the Raycaster. That's something we could totally do and probably should eventually. But to actually test any individual piece of the algorithm is quite difficult, because the only way to know what the result should have been is to have a properly working version of the routine. And if we had a properly working version of the routine, I'd just use it, right? Now, sometimes you can look at unit testing a little bit differently and say, well, we're not really going to think of it as a unit test, but we're going to think of it as sort of two wrongs make a right. We're going to write the routine once, and then we're going to write it a second time a completely different way, and then we're going to keep working on them till their answers match, right? And that can be a valid strategy. If you have something that's really difficult to test and you don't really have a way of testing the answer, but you really need some way of finding the bugs in it and you don't really have any other options, you can definitely try to go that route. But with something like Raycasting, it's inherently very visual. Your eye immediately knows whether something is correct or not in a way that writing a test is very difficult to do. If I can pick a node of the voxel, see the outline of that node, and then see the outline of the boxes that it included, it will be immediately obvious to me what it is doing. And more importantly, and this is something that's important to understand that unit tests often can't tell you, it will also tell me how it's wrong. Because when I can visually see what is getting included in that box and how it's getting clipped, I immediately also know what's wrong with it if I don't see what I expect. If boxes protrude too far outside of it, then I know they're not being clipped properly. If boxes that aren't inside it are included entirely, then I know that the bounds checking is wrong, right? There's a lot of things I can intuit from seeing the visual version that a unit test simply doesn't tell me. A unit test just tells me whether the results agreed or not, but it doesn't necessarily have any way of telling me in an intuitive way how those results were incorrect. And so again, especially for something like a game where you do not actually have correct answers sitting around, you don't have a corpus of testing, a lot of times visual testing is much better than unit testing, because visual testing both provides you a way to quickly see whether the results are correct without having to try and figure out another way of doing the algorithm that will somehow magically be more reliable but just slower, I guess. So that's why you're not using it as your actual algorithm. But it also provides you an intuition that you don't have otherwise. And finally, it also gives you something else that you don't have with unit testing, which is insight into the problem that you may not have had otherwise. So once you start drawing things that are visualizations of the problem that you have, you may actually gain insight into how to solve the problem better. And a unit test can never really do that for you, because all a unit test is going to do is tell you whether or not the code worked properly. It's not really going to tell you anything that you didn't already know about the code, because you're the one who had to write the unit test for it. So obviously you knew what you were doing when you wrote that. So having a visualizer that can draw the various aspects of the algorithm to help you find the bugs can also help you improve the algorithm, and that's a really important thing to keep in mind. So when choosing between doing something like unit testing and doing something like visualization, I would argue that visualization is usually where your time is better spent, especially in a game environment where a lot of things are very poorly defined and don't have really good right answers to them. A lot of times, if you have success with unit testing, it's usually because your problem is very simple and has a very simple definition of what the answer should be. And in those cases, it may be totally fine to do so. But a lot of times, that's just realistically not what you're doing. Games are much more complicated than the things that people typically write unit tests for, and have much more fuzzy definitions of what is correct. So it's much harder for you to do things like unit testing on those. All right, so let's go ahead and try to put in some visualization for what's happening with the grid Raycaster here. So I think what I'd like to do is kind of re-invoke, if you will, the debug idea that we had before, where we would sort of say, look, we know that if we drew everything, the Raycaster's Raycasting tens or hundreds of thousands of rays every frame. We can't draw all those. It would just be a giant mess on the screen that wouldn't tell us anything. But what we can do is just randomly pick one location in the world and say, let's look at one of the rays or a couple of the rays that are coming out of that one location. And then we can sort of get an idea for what the raycaster is doing by looking at that specific ray or that specific grid. So what I'd like to do is something here where we'll just say, okay, let's go ahead and say if, or maybe we'll make a Boolean value that's like debugging, and we'll say if the initial grid index equals some value that we set. So we can set this grid index to whatever we want, right? It can be anything. We'll just set it to something, and then we'll look at the rays that come out of this specific grid index and this specific grid index only. And furthermore, we can do some more specific testing here if we'd like to and limit the actual number of rays we look at. But for the moment, I'm just going to draw them all from one specific thing, and then we'll start paring that down as necessary. So what I'm going to do first is I'm going to draw, for our debugging purposes, I'm going to draw the ray itself. And I'm going to do also draw the voxel region that the ray exists inside. So we cast this out of the center of a voxel for a specific reason. We wanted to compute lighting that occurs within that voxel, and the center seems like the best place to do that since we can only compute it out of so many places. We're going to draw what that box is, and then we're going to draw the ray. And so what I'm going to start with here is I'm going to call the push debug box call, and I'm probably going to get rid of this if here. It was probably just there for some quick testing where we didn't want to draw too many boxes or something like that, but we want it now. And so what I need to do is I need to produce a few things. I need, first of all, the color, which I'm going to use, I think, cyan for this particular, like the starting box area. And then what I need to do is I need to produce a boxmin and a boxmax for the voxel. And in order to do that, I'm going to need some way of asking the voxel what those bounds are. And fortunately, I actually have a way of doing that, which is get cell bounds. Now, it's a little bit difficult for me to produce that because we currently don't have a way to reverse engineer an index. We have flat index from, but we don't have sort of the reverse of that. So now would be a good time for me to write that. I didn't write it before because I was like, well, I don't know if I really need it. I do think we need it for debugging. I don't know that we ever need it for any actual work, but that's okay. Building debug things into a game is important, so I don't mind doing that at all. So what I'd like to do here is I'd like to say, okay, if we're doing the debugging, I would like to get the cell bounds here. I also don't really understand why I need to pass a boxmin and a boxmax to this when I have a rectangle, so I think I'm going to have a voxbox there that I can just pass, and then I'll have there be a version of push debug box that unpacks that for me. It just makes my life a little easier, which seems good. So in here I know that I want the spatial grid. That's the grid that we're actually looking at. And in terms of the index, again, this is not quite correct. So what I want to do here is I want to say triple index from, or however we want to look at it, maybe XYZ index from, or dim index from maybe, and then I'll pass the initial grid index. So this way I can figure out where I am in the voxel like so, and that will help me out, right? So I'm going to go now look at how I would write that function. So we have flat index from, and we know that that's how we produce the answer. So if you look here, we go, okay, we take the cell count x, and you can see what we do, right? The x is the step by one, the y is step by one whole x row, and the z steps by one entire xy sheet, right? So what I want to do here is I want to produce a version of this that does the opposite thing. So I'm going to call this dimension index from. That gives us back the v. So I'm just going to swap these two, right? There's the v3s, and here's the flat. So my goal here is to take the flat index and somehow produce the dimensional index from it. Well, I know several things about this. First of all, I know what each of the sheet dimensions is, right? Because I know that, for example, the z sheet size is just going to be the cell count x times the cell count y. So I know how many there are on a z sheet, and I know that the only way to get that far into, to get one whole one of those forwards is to move in z. Because between moving in just x and y, if z was 0, I would never get out of that initial first z sheet. So what I can do here is just divide and get the answer. So if this is how much is in a z sheet, and again, I will pull this out for convenience so I don't have to keep using the arrow. So what I can do here is say, all right, whatever the input index is, so when I look at this index, if I divide it by the z sheet count, that's going to be my z, right? Because however many full z sheets I went forward, that's my z answer. Now, if I then want to take and decrease the index as we go, I don't really know that I want to modify it in place, so I think I may create a new one here that's like index remaining, right? So what I can do here is say, okay, let's take the index remaining here, and we'll divide it by z sheet. Then I'll take the index remaining and I'll subtract whatever that value is that I got times the z sheet. So that just gives me however much I have left. Now what I can do is say, all right, finally we know there's a result y, right? And the result y is going to be just however many x rows, we went forward, that's the y value. So I can again take index remaining and see like how much is a y row. And a y row is just going to be cell count x by itself, right? And so then I can say index remaining minus equals that value. And then finally, I can say, okay, the remainder of that is just going to be my x, because whatever I have left after removing the sheet motion and the row motion, all I'm going to have left is just x, right? So now, this is not a particularly efficient way to do this. I could probably do a better job of it, because I don't really need to probably do full divides on these. I could be a lot more clever. Furthermore, I could just demand things like that the grid was always powers of 2, in which case I could just use masking and shifting to get the answer. But again, we don't suspect that we'll ever actually call this function in any real sense. It's just for debugging, as far as I can think. So anything that gives me the answer is good enough. And in this case, that should give me the answer. So I'm going to call that, and I'm going to push the debug box in this case. And then I'm going to go ahead and say, look, let's make that debug box function a little easier to call by taking a rectangle. And then we'll see where we get with that. Okay, so this just calls push debug box, solution, box.min, box.max, box color. And then this, instead of taking a v3, is just going to take a rectangle. And so that's just like a semantic improvement for my own purposes, right? Doesn't really do anything else. Okay, so now when we look at this, what I want to try and do is make it so that I can, pick out where the heck this debug box actually is. And there's a couple of things we're going to have to do with that. Like I don't see it right now, right? For example. So what I'm going to have to do, first of all, is we have to make sure our debug line drawing is still working, because we made some changes to that, and we don't even really know if that's working properly. I also don't actually know what initial grid index 47, I assume that's something, we should be able to see anything that's not larger than the total grid or whatever, right? Oh, actually, no, that we have to make sure we're at least not on the apron, though, because the apron never gets casted from. So actually, we do have to make sure it's something. We could very well pick a number that never gets drawn. So I'll have to set a breakpoint there to make sure we do actually draw. Didn't think of that. But we also don't really know if we're still going to draw that, because, looking at I don't see it, it could be that I just don't see it. But it's also possible that we messed up the debug line drawing. So we have to make our debug system work reliably here. And then we have to make sure that anyone's actually casting this. While we do that debugging work, I'm going to switch to debug builds. So I'm just going to set this to an OD here. And then we're going to step into there and make sure that it's working at all. If I grab, where's the lighting file? Hello, Remedy. There we go. So if I take a look at this code here, I just want to know, like, do we ever get in here, right? Because if we never actually get into this piece of the code, then I know, like, oh, whoops, we must have picked something on the apron or something like this, right? And so we're never actually stopping here. So it looks like I got to go find out, like, why are we never hitting this path? Like, why is initial grid index always weird? And obviously that could be a bug, but... so here's our grid indices here. I guess now that I think about it, like, the initial sheet would be like, what, 24 by 16 or something? So if we're not above 384, you're not going to hit here, right? It's weird that that's the first one that hit, but that could just be a multi-threading thing. Anyway, we know that 4667 is a valid thing because I just watched it come through there. So let's start with that, and now let's make sure that we're actually getting back something reasonable and trying to push the debug box on. So here we go. We should now hit the inside of this routine properly. So if I remove this one here, we should hopefully get to the inside of this at some point. There we go. And when we ask that thing for the cell bounds, we should get a Vox box here, and you can see that we actually do, right? So that's good. Now, there is something that I don't know if we ever actually addressed. So in this code, when we call push debug line, yeah, so you can kind of see here, like, there's some problems we're going to have if we actually want to run this, because we are running it multi-threaded. Now, I'm pretty sure that in fact, I know for sure. So only one thread can ever process a particular voxel region. So I think we don't have to worry about the fact that this is not thread safe. You can see here that we're just incrementing this thing, and we don't use a locked increment. So two people could overwrite each other. I think we're fine there because, again, we're not really calling this from multiple threads, even though multiple threads are running. So I don't anticipate an issue there, but I just wanted to point that out because if we were going to call it from multiple threads, we would get some dropouts potentially as two threads hammered on that value and didn't sync up, right? We would want that to be a locked increment. So if we go ahead and run this program now, now what we want to do is try to make sure we can actually see that. Okay, so we do. So here's an example of a place we're casting the rays from. And again, remember, we've done absolutely no work yet to make sure that we only cast rays from voxel cells we actually care about. At the moment, we're actually casting rays from the entire voxel region. And in the future, we may decide to try and limit that, but we might not. And the reason that we might not is simply because we will have cases where we'll be pretty dense throughout that region with things stacked on top of each other, and we don't want the game to like have too much of a variable frame rate. So I'm not certain that we'll ever make that change. We may not. But that's okay. So now we know that we're able to draw our debug lines properly. So now what I want to do is instrument the rest of this code with actual, augmentation of the raycasting. So what we're going to do here is, first of all, we want to draw, in addition to this debug box, I'd like to draw the actual ray. And what I'd like to do is sort of draw it in two parts. I don't think I want to draw it here. I'd rather draw it sort of maybe down here more after the hit detection has occurred. So maybe like more down in here. And what I'd like to do is I'd like to draw two debug lines where I show in one color I'll show where the ray starts to where the ray supposedly hits something. And of course, in this particular case, we know it won't hit anything because that's the bug we're looking at. But eventually, as we go, we'll probably want to debug actual hits as we get closer to having the routine work properly. So I want to draw one thing from where the ray starts to where the ray hits, and then one from where the ray hits out kind of further, just so we can see where the ray actually would go in case it hits really close and we can't quite see the ray. Like, we get like spurious. I want to see where it would have cast out to, right? So it's just showing us those two things. All right, so let's go ahead and push the debug line on here, and you can kind of see that function just allows us to pass 2 points in, right? So we'd say what color we want and the from and the to. So here's the the ray origin to the hit P, right, is one thing we want. And then we want the hit P to like the far P, right? So that's what we actually need. And the colors for that, let's say that the hit line is like yellow, right? And then maybe like we'll do a dim version of the yellow, kind of going far from there, or maybe it's like kind of more of a red line. I don't know. We'll see. More of an orange. So what we need to do is we need to compute these, and obviously the grid raycaster is easier because it's casting one ray at a time, which is really nice, because that's the way we structured it. It's one ray against multiple bounds. The old way was multiple rays against one bound, so this is easier for us to work with too, which is kind of nice. All right, so it's ray origin single, and then the hit P, we need to know what the actual P value was here. And so I believe if we look, when we terminate out of here, you can see that we have a T-ray value, and well, in fact, when we actually call the probe N single, probe P single, that's actually produced the hit, right? So I think we actually can just piggyback on top of that. I guess we don't really have to compute it ourselves. So it'd be probe P single is actually the value, at least for now. And then when we want to draw the rest of it, we just draw from there to something like that's just far out. So like far out, man. So, you know, 50 units or something out in the direction of the ray. I don't actually know what the ray direction is here. It's going to be, so ray D single is the actual value. So that's just me trying to draw the ray. And so now what I should see is, if I run this, I should see the rays casting out, but only from that particular one. Yeah. So here you can kind of see those going. Now, one really interesting thing you can see is we obviously screwed up, right? Right off the bat. And this is why I say it's so good to have visualizations. You can see, like, right off the bat, we're only casting rays in one sort of conical direction. And that was definitely not part of the algorithm. So we're supposed to be seeing a full sphere here of things happening. And we're not seeing that at all. We're seeing some kind of a like, you know, restricted to only, kind of hard to say. It looks like maybe we're getting kind of like only positive directions in Y, but you know, it's really hard to quite read what the bug is there. But you can see, like, very clearly we've got a bug where we're not actually getting spherical results here, right? And we should. So before we go any further, it's pretty easy for us to start looking at what that problem is. Okay. And remember, we're drawing these rays no matter what. So when we come in through here, like, we don't care whether this loop terminated with a hit or terminated on cost or terminated because it ran out of space in the grid. We don't care. We're always drawing it. So in theory, we should see the full sphere of casting because we draw all the rays that there are from this particular voxel, and we're totally not seeing them, right? So we know there's something bogus going on. So we have a couple of different things we could look at. If I look at the sphere generator, that's obviously the first thing that could be busted. And if I go look at how it's actually outputting things, I can just maybe start to look and see if there's any obvious errors here. So you can see that the way this is working is we step through the octahedron and we look at the number of rays per octahedron that we want, and we just output those in order, right? So we just kind of go through and we output all of the octahedrons kind of just packed, right? And there's a couple of different ways that we could be messing this up. One is that it could be that like none of the rays in this entire array are actually pointing in the correct directions, right? Like they're all sort of pointing down in that sort of one direction. And so it doesn't matter where you're sampling in the array, you're always going to get something pointing in that one sort of general conical direction. That's possible. But the other thing that's possible that we have to consider while we're doing this is that maybe there are correctly distributed rays in this array, and we're actually only sampling a few of them. So we've got the range wrong, right? So there's two ways we could have screwed this up, and so we want to kind of look at both of them. Now, since this produces an INL file, I should be able to go in here and look and say, all right, so here's the total light sample direction. If I look through these, I should see a fair distribution of signs. And specifically for Y, I should see like a distribution of signs. It didn't look like I was getting that. And when I spin through here, I do see a good balance of signs in here. I can't tell from visual inspection whether these are properly distributed around the sphere according to the octahedral map, but what I can tell you is that there do exist some positive and negative Y's, right? You can see them very clearly as I kind of move through here. And so if I was seeing a biased distribution, I wouldn't necessarily be able to say that it was broken or correct just by visual inspection. But when I look at this, I can see that I'm literally never casting anything out in this direction. So I pretty much know that it's not just the values in the array that are wrong. There's something else wrong. And it could still be that the array is constructed improperly, like perhaps there's too many of a certain kind of value and we're only sampling from one part of it or something like this. But we at least know that the values in the array do contain other directions, and we're just not actually using those directions. So let's take a look and see what we're actually getting here for that. And also, by the way, when I look at this, there's another thing that I wanted to kind of point out as we're going here. So one kind of bizarre thing, if we look at this, I'm not sure why we're getting like a black versus a yellow. That's just really kind of nonsensical to me because I put in, a totally valid color value here, but I'm not really getting one. So I'm not sure why that. Oh, I know why. So that may well just be because of lighting, I suppose. So if I look at where this is, yeah, you know what, that probably is what it is. So this may just be because the lighting itself is, right? You can see I'm crossing out into the unlit region, right? So that's why the lighting changes there. That's what's actually happening, right? Which is kind of just yet another indication that we probably need to go and actually put lighting on and off into the renderer because we don't have that ability right now. Everything always gets lit. Okay, so what I'd like to do now is take a closer look at why we're getting that particular bug. And I guess it's an important bug for us to do first as well, because if we do want to if we were going to look at why this thing was never hitting anything, well, it actually isn't. We need this thing to cast a ray up in that direction before we can figure out why it's not hitting anything, right? So actually, for this particular grid cell we happen to pick at random, the reason it's not hitting anything is because it actually isn't. Like, it's actually getting the correct answer, oddly enough. So let's try to figure out what's going on. If we look at where these rays are coming from, inside the grid Raycast routine, we're actually feeding them using this sample dir here, right? And the way this works is the sample direction comes out of this octahedral table, and then what we're doing is we're looping over these. Now, I mean, if I look at what's going on there, I can sort of almost already see that it seems a little bit broken. Because if you come through here, remember, we're going to be casting 4 rays at a time. And so we're going to be taking the sample direction and indexing 4 of them. Then this passes just that same thing plus 1, which is not going to cut it, right? So if we're sampling 4 rays in the grid cast, that needs to be a plus 4, and this would need to be a plus 8, right? Because that's the actual striding that we're using there. Now that might completely explain the bug, actually. Let's see. Because that would be enough right there to screw it up. Okay. So now if we look at it, we're seeing a much more sensible raycasting distribution, right? There's some issues here, and I think these are to do with our generator table just running out of picks, and it's probably producing the non-jittered version. There's actually to-do in there for it. So you can see there's a little bit of bias in a couple of these rays that we probably would want to get rid of. But on the whole, it now looks relatively good. I mean, that's not a horrible distribution of rays. You know, maybe there's some things we would want to change about that, but on the whole, that's okay. And so now we just need to start wondering, why do these rays never hit anything? And in the region where we actually have full lighting happening, you can actually kind of see that we're pretty clearly not hitting anything either, because these are still bright yellow going up through here. So even before we've added any of the other debug rendering stuff that we want to add, we can kind of see very quickly that this isn't working. That should produce a pretty obvious result. So what I'd like to do now is I'd like to just take a look and see if there's an easy way for me to sort of limit the number of rays that we're actually casting. And what I'm going to do here is maybe just control, say, the direction a little bit more. So what I'm going to do is say, look, if we're debugging, I want to take the inner product of the ray direction. And I guess I kind of need to do this a little bit further down now that I think about it. So I probably want to do that in here. And I probably also want to so I guess I'm going to call this ray debugging. And what I'd like to do is I'd like to make the drawing of the ray itself be specific to this particular ray direction, basically. So when we get down here, I'm going to look at ray debugging as opposed to the regular debugging flag. And that way I can limit the number of rays. And the way I'm going to do that is right now I kind of want to look at rays that are casting upward. So I'm going to say that, like, if I take the inner product of the ray direction, and I guess I really don't even have to quite do that. Maybe I'll just say, look, let's look at the Z. And if the Z is greater than like 9, we know this is a fairly straight upcast, and we'll look at that, right? Let's do it like this. So this is just me limiting the rays I'm looking at a little bit more. And so you can kind of see now, if I go look at this, I'm just kind of looking at the rays that shoot upward. And so that just gives me a better, you know, a more focused way of looking at how these things are being cast, right? And now what I'm going to need to do is add a little bit more debugging in here so I can see what we're actually doing. So for starters, I'm going to expand on this code here where we're actually drawing boxes to draw which boxes we visit. So when we look at this, when we get these nodes here, the lighting spatial grid node is looking up off of this grid index. So what I'd like to do is I'd like to just draw for every time that we enter here. If we're doing ray debugging on this particular array, I'm going to grab the Voxbox for the grid index we're on, and I'm going to draw that as like, you know, a candidate. And so what this is designed to do is this is designed to tell me, are we walking the grid at all correctly, right? And so one of the things that you can see here is right off the bat, like, unless I just did something stupid in that code, I'm not getting any actual drawing. So what I'd like to do is take a look at this piece of code and find out why I'm never getting in here. Because we know that ray debugging is set to true sometimes because I see the rays getting drawn. And so either this code is somehow erroneous, or we're always terminating this loop immediately, meaning we never like go past the starting node, right? So let's take a look at what happens. I could also do sort of one other thing here, which is I could choose to draw the starting node a little bit separately, a little bit differently. So let's say, for example, that I do an add radius to on this particular Voxbox, and I just say, you know what, let's go ahead and shrink it in a little bit by, you know, a quarter unit. And that would allow me to see whether we're even looking at the first one. Just visually, I can see right away, like, are we even looking at it? And so what you can see here is when we're drawing this, you can see pretty clearly that I'm getting both of those two things. So I'm drawing both the starting box, and I'm drawing that box again in here. So we do correctly come into this piece of the code. And what's obviously happening here is somehow we're always terminating immediately. So in the actual square we start from, we're terminating, and we're terminating with a no hit. So for some reason, we terminate prematurely for sure. And I'm not sure what that is, right? Like, so yeah, I don't really know. I'm just going to step in it because it's pretty easy now for me to do that. So that's what I'm going to do. But yeah, I'm not sure why we're getting that result, but it should be pretty obvious, hopefully, if we just step in here and check. So let's go to the first time that this happens. And one of the problems I'm going to have, I should probably switch this up, is this is running multi-threaded. It's going to be a real pain in the butt. In fact, you can see it being a pain in the butt right there. So I may need to go to the internal core here and turn off the multi-threading at the moment. So you can see this lighting queue value here. If I don't pass a lighting queue to internal core, it won't run multi-threaded. So if I want to here, right, instead of passing lighting queue, I can pass a 0. That would allow me to not deal with the whole, like, n billion threads are coming through this path, right? Although, it is a little odd because no other thread should have had ray debugging set to true. So that's a bit weird, to say the least. So that makes me a little nervous, because that shouldn't actually be the case. It still would have been a pain in the ass to debug, pain in the butt to debug, but I wouldn't actually have suspected what I saw to be true, which was that I wouldn't have expected to see a second thread hit the Ray debug unless that's not what actually happened. So that's a little concerning. And we may want to keep that in the back of our minds as something to investigate in a second, but I want to keep investigating the thing I was going to investigate first, just so I can see. So when we step through here, we see that there are no leaves, and that's exactly what we would expect because there shouldn't be any leaves, right? If there were leaves in this particular box, that would be odd because we just looked at it and there was no geometry in there, so there shouldn't be anything to test against. We also don't expect something hit to happen because we didn't hit something, so that's good. And then it looks like the cost metric has decked down to 0. Oh, all right, that's just a typo. So this should actually be if cost metric equals 0, right, or is less than 0. That was just the wrong way around, right? So that's just stupid. All right, so that's one bug down. Not a particularly interesting one, but at least it is one. And now we can see, I suppose, we should be able to see this thing actually step through something for real. Let me run through here. So now we should see it like, yeah, right. It should be moving forwards correctly, and it does. Okay. So let's switch back to at least optimized, and probably also, unfortunately, we gotta switch back to the fully threaded version, just because lighting is so darn slow. There we go. And let's take a look at now if we're actually drawing a grid walk, because that would allow us to figure out if our grid walk is busted. So that's one of the things oh gosh. Okay. Well. So I guess what I would say is, yeah, so we can obviously see something wrong with our grid walk, which is great because, again, like I said, visualization tells you what your bugs are very quickly. It's another really great part of debugging with visualization. So what we can see here is we know that we should have been walking upward, but instead we're walking downward. So what I suspect is we have some kind of a sign bug in our walk table generator. And, you know, we haven't really looked at this routine. Remember, I said there's multiple routines involved, and all of them, or, you know, at least 2 are probably buggy, and they are. So what we should see here, if we take a look, we should be able to figure out here why we're getting the wrong stepping. So let's take a look. So here we are, and you can see us walking through each sample direction. And we pull out a particular sample direction, right? And we set and say, well, wherever we are, we're going to start writing to that particular part of the walk table. So that seems reasonable. I mean, we're going to have to double check that part too, because it could also be that we're picking the wrong offset in the walk table for a particular array. So that's also, you know, something we could try to verify. So in here, what we see is we've got this step value and we've got this dim step value, which is how much we would step in any particular direction. And what you can see here is we go through the dimensions and we look to see whether the ray is going in a particular direction for that specific dimension, right? And what we do here is we say if the ray is going in the positive direction, then we set the step value for that dimension to equal to the step. If not, then what we do is we make the ray be positive anyway, so that way we don't have to worry about different ones. But then we set the step to be negative, right? We then multiply the step by whatever the voxel dimension is in that particular direction. And the reason we do that is because obviously it's a step by more and more each time as it goes from X to Y to Z stepping. To be honest, that seems fine. I can't say I can immediately see what would be wrong with that. But let's keep going. There might be a bug in there. I'm just not sure what it is. We start at the starting location and we look to see if we've gone, how far we've actually gone. We don't want to go past what we know the Raycaster will never actually use. We start by figuring out what the best stepping would be and which dimension that would be. We go through the dimensions and we say, if we were going to get, so we take the cell dimension, so how far we have to go for a particular cell, and we subtract the location that we're actually at so far in the cell, which I believe gets initialized to the center of the cell. Yeah. We then divide by the ray direction, which is the stepping rate, right? And we see how far in t we'd have to go before we would cover that specific distance. We figure out which one that is, and we set the delta to that step, right? Which we pre-computed before. And we move the ray by that much. Which is wrong. So the problem with that is we aren't removing that element of the cell dimension from our position. So I don't think this actually would cause the bug. So we have another bug that is not related to this. But because we're just solving this locally, we need this at value, right? We need that to constantly basically modded by whatever we're stepping, right? So, not sure how to say this right, but basically we need this to take whatever the dimension that we chose, so like the best dim, and we need to subtract the cell dim so that we recenter ourselves, right, with respect to that. That way we're constantly just inside like one cell, and when we do this comparison, it will actually work. I don't think that will help here. That's just a separate bug, right? But this is like a directional problem. So the reason I didn't think that would solve this bug, and I was right, is because this is a problem with even the very first step, which this fix only would only address bugs that happened on subsequent steps. So the question is, for a ray that's clearly going upward, which would be what, positive z? Why are we stepping backwards, right? And I really don't know. We're taking the ray direction from the sample direction for each one of these, and we're writing the walk table offset as whatever we're actually going to write into, correct? Yeah. So I'm not sure what's wrong there. The dim step here is set to 1 and should only become negative in this case. I mean, it should only become negative if the ray direction is negative, but we're sure that it's not for this ray because we literally are only looking at rays that have a z greater than 0.9, so no way for it to be negative, pretty obviously. So how is it that we're getting a negative step? Is the dim step part of this somehow wrong? That's one thing. Or am I overwriting or writing to the wrong place in the table, right? Because if I'm looking up the wrong place in the table, obviously that would also be an issue. So let's just see how we pass the table around in this particular case so we can see if that feels right at all. So if I do a search for the, just for the walk table. So you can see here, I'm taking the walk table offset for my particular sample direction, right? Which is the thing that I, in theory, wrote right here. And I mean, it sure seems okay. So I guess I'm also just gonna have to, maybe the best thing to do here is just to go, look, let's watch the walk table be built for this particular array, and we'll just see what it gets. Because yeah, I don't know, it looks fine, right? I mean, it looks like what I would think. So let's do this. Let's use our same method before for debugging. So in here, I'll just nerf this out. And I'm going to go ahead and watch the walk table get built. And what I'd like to do is be able to, just see which, for one of these guys, somebody who's one of the arrays that we're actually debugging, and I don't know which one it would be, right? Excuse me. So for one of these arrays we're debugging, I just want to see what the direction index actually is, so that when we pull out, when we pulled out this walk table, like what was the actual walk index. So if we look at sample directions array index, what is the walk table offset? Okay, it's 0. So, I mean, that's pretty obviously wrong. Like, why is the walk table index 0 for everybody? So something's up here. Wait a second. Yeah, that's just really bizarre. So let's take a look at how that's getting initialized. So something's really busted here. And let me just remind myself how that. Is there an obvious bug in here somewhere? So here's dest index. Nice. So yeah, we were just never generating any of the walk table, actually. Let's see what it looks like now. We're never going to run here because we're running single-threaded debug, which is about the slowest possible thing one can imagine. So I should probably switch that up. But wow, that was kind of crazy, right? Should probably make a switch for this that quickly turns off debugging for this purpose. It's just dumb. Like, this is the kind of... You can kind of see why it's so annoying to do engine programming is because if you think about how many tools people have built for like crappy, lame programming, like JavaScript or something, there's so many things they can do because people actually built tools for it. Whereas really basic stuff you would want to do. So for example, one of the obvious things you would want to do is write your compiler so it's not terrible, so that when you're debugging, you can swap in the debug version of that routine to step through instead of the optimized one. This is actually very easy to do if you actually cared. And it would make it so simple to do this kind of debug work. You would just literally have a button in the debugger that would be like, patch the IP address over to the other routine now because I want to step through it, right? But of course, like, forget that. Like, I'm talking about space age technology, you know, as far as Clang and Microsoft are concerned. Anyway. Okay, so now at least we are properly getting some walk stepping here, but you can see that it's still wrong. So it's always picking to step upward, but upward is not correct. So we've still got some additional issues. I don't know if that is actually a bug in the stepping code, though. So let's just take a look at the grid Raycast code to see, you know, like, how are we actually stepping? So you can see here, like, the walk table is not getting incremented, right? So we need our walk table to actually update. And so this might just be because after we use it, we need to do this, and we aren't, right? Okay. So now that's actually looking quite nice, right? So now we can actually see that we're getting, you know, a variety of Raycast here. And there's some weird things happening with, I don't know why that's occurring, right? So that's a little bit strange and probably merits some attention. Could actually have to do with if that's part of the drawing of the hit p-value or things. So that's fairly disturbing. Right. If we look, though, at the actual way in which we're stepping through this particular part of the grid, it actually, like, at first blush, and we'll have to pause this later so we can watch these things more carefully, but it actually looks quite nice. It does appear that the rays are aligned with the grid stepping that's occurring, and I'm pretty happy with that. So I feel like we've at least debugged a significant set of the bugs in here that we had, and we're now kind of getting down to a difference, you know, a separate wave. So I'm pretty happy with that. I think that's pretty good. So what we need to do now that we can sort of see that our rays are casting relatively correctly and we're walking the grid relatively correctly, the sort of final thing I want to do to let us start to debug the actual literal raycast part of this is I need to now kind of be able to focus in on only just one ray. So if I want to focus on literally just one ray, I'm going to need some way of maybe passing in the debug value from the outside. Because by the time I get in here, I know where I'm casting from, but that's really all I know. And so I need some way of making this a little bit more, I guess I could make this part a tighter bound, and maybe it would be sufficient. I'm not sure. So maybe if I did this, you know, we can just kind of pick some arbitrary stuff here and grab one that way, but passing it in from the outside might be like the better way to go, right? And so here you can kind of see it, you know, doing the debug cast. But again, I think that's kind of a fool's errand. at some level. So I think what I would probably rather do is just do a forced debug call at some point. So rather than do this, I think what I would do is I'll leave this in place. I'll turn off Ray debugging as a thing. So this will just, again, use the debugging call. And what I'll do here is I will kind of go, I think I'll kind of go with maybe like, just do the first ray from the bundle. So, you know, in here, we'll just say debugging equals false, right? And in addition to just doing the first ray from the bundle, rather than using this, I'll pass in debugging as a thing. Then I'll just pick one to do in the outside as a separate part of the routine, right? So in here, I'll just go ahead and, as part of the, let's say part of the main Raycast, I guess. I guess I'll do it as part of fullcast. So as part of fullcast, I'll do the check there. And in here, so, you know, you can see it's kind of looping over with the voxel center P stuff here, right? I think what I'll do is I'll do an additional one here. So I'll just say, all right, you know, like we'll let it erroneously write. So this is just like a debug system thing here. I'll let it erroneously write into something here. So we'll say like, sure, like whatever. The tile that we're writing here is just, you know, this random spec tile. And then we'll pass the rest of this stuff by picking out a specific one of these. So down here, I'll say, all right, there's going to be like a debug dir, and it's going to be like something out of the set here. I don't know which one we want to do. We can pick anything we want for this, and then we can pass the, you know, all the stuff here. So I can pass the ray origin. I can pass the ray direction, which actually take it back. I can actually just do this. There we go. And all this stuff should be roughly the same. So I can pass the ray origin single, which we know will always be the same. Spec atlas, diffuse atlas are the same. Spec text is the same. So now I just have the debug dir is what I'd pass here, right? And what I can now do is just wrap this in the if initial grid index equals something, right? I don't remember what the value was, but we probably want to pick one that we actually want to test. This will do one raycast with debugging turned on, just one, and it can do the same one every time. So up here, you can see that we use the entropy index for the octahedron. That's what gives us the jitter. So here instead, what I can do is set this to something, right? Maybe I use 0 for it. I don't know. We can pick which one, but you know, we'll see as we go. So if I run this now, what I want to do is pick one of these grids and pick something that's I want to pick something that's actually going to hit, right? And so what I can do is try to like find that just by trial and error, because we don't really care. But again, we just need something that's going to do like a proper hit here. So when we take this debug dir, I could just say, look, let's add something to the debug dir, you know, plus, I don't know, 20. Who knows, right? But we can just pick random numbers until we find something that actually casts in a direction that we can use, right? So that's almost good, right? It's not quite right, but it's almost good. So let's maybe try a little more here. So that got worse. Let's try backing it up. Yeah, I really have no idea what the correct thing is to cast on here. Not sure why that didn't give me something useful. I need to add this to like some kind of hotkey probably, right? Maybe I should just move which grid we're doing, since everything I'm picking seems to go downward. I think there should be what? Like, if there's an 8x8, right, there should be 64 of these light samples. Is that right? And yet, literally, like, no matter what I pick, it seems like it doesn't go that direction. How is this possible? This is really annoying. I don't even know why that would work that way, because if it's the octahedral map, it should be walking along an octahedron, right? I mean, each one of those should be, right? Because if you remember inside HH sphere, right, the way this thing was lined up is it generates a Poisson distribution, and then it comes through here and says, well, as I'm picking these, we pick a specific txty each time and step through, right? Tx, right? We go through those and we look to see, you know, as we select them. It's the 8x8, right? So there should be 64 in each octahedron, right? And we should have them correspond to the actual, like, to the actual octahedron map layout, Tx and Ty. Now, it should be such that, like, 4 times 8 plus 4, so it should be, like, probably something like 36. Should it be sort of towards the center, right, of the map? Okay, well, all right. I guess thinking it through paid off in this case. Yeah. So let's try that again. Now, one interesting thing about that is, like, I'm sending that down, but it looks like it's not correctly getting the walk index there, right? Did you notice how that was wrong? It looks like it's still going downward. So this will be interesting to see. But anyway, so looking at number 36, and then telling it to debug that, grid raycast, that gives us one that should hit and that we can walk through, but why? That looked wrong again, right? Like, that looks like an incorrect walk value. And that may just be because it didn't, like, generate the table or something, because we haven't really looked at that. Yeah, okay, so it's fine. Because doing the hot code reloading on, I don't know what happens with the tables on there. We haven't really looked at that. So if you take a look here, you can kind of see the ray as it is passing up through geometry now. And so what I'd like to do next is just see what geometry it actually is trying to collide against. So I'd like to see, you know, for each one of these boxes, I'd like to see which ones have leaves, first of all, and then go from there. Now, again, I think I'm going to have to do, I might have to make the remainder of the stream, rather than debugging, actually just be fixing our lighting code in the pixel shader, because like this is not useful. You can kind of see here, like, well, those two things were sent with separate colors and they look the same. And that's going to be a problem because it means we can't use color as part of our debug information, really. And we kind of need to be able to. So like, if I just look, you know, at what I've got here, .5, .250 and 1.1 should look different. And similarly, oh wait, no, that's okay. Never mind. Let me go ahead and see what happens if I change this. Oh, no, I did. And so 0.5, 0.5 should look different than 1.1. But it doesn't, right? So it's just kind of busted. Like, you know, it's not working correctly. And so I think we're going to have to figure out something to do here. Now, you know, we've been avoiding this for quite some time, and I don't think we're going to be able to get away with it forever. So, like, you know, that's just not sufficient. So maybe that's what we have to do now before we go any further, because without being able to push debug stuff on there, you know, so I think we kind of need that. What I'd like to do is let's go ahead and go to the pixel shader side of things. So in the OpenGL like ZBias program, which should be here, you can kind of see like, all right, as we come through here and we do our lighting computations, really all we need is just a constant that turns this on and off, right? Since it's really only for debug purposes, we don't really have to care too much about it in terms of performance, probably. But so when you see here, when we've got like if lighting disabled, else, and you can see the surface reflect times thing. So this world Z, this was the hack that we had in there from before. And that was for this stuff, right? So that we could overlay this stuff on there, right? And that works well enough, but it was just a hack that someone suggested, and I was like, okay, I'm fine with that. But I think what we'd rather do here is we'd rather have a constant that lets us determine how much lighting you actually apply, right? So what I'd like to do is maybe something that looks like this. So let's suppose we say, you know, we have surface reflect is the value we're going to actually have here. So we have the like the lit reflect version is going to be, oops, I deleted the sum light by accident there. There we go. So what I want to do here is say, okay, surface reflect is going to be times equals L, but what I'd really rather do is just have one multiply in there or one lerp in there that lets me control that. There's two really ways we can do this. It's really hard to say, but based on the way graphics cards work now, I'm going to say we just want a constant that controls that. So we probably want just like, you know, lighting enabled is an actual Boolean. That's probably the fastest way to do it these days, because usually what will happen, I think, is that modern graphics cards will actually look at those constants and use them as actual switching on and off. If it's entirely one way or entirely the other way, I think they'll actually handle that. Don't quote me on that. I don't really do much with this kind of stuff day to day, so I'm the wrong one to ask. But I think if you want to say like, okay, there's a uniform, oops, there's a uniform int that's like lighting enabled, and you pass that in, and if you have that on, you get lighting, and if you have that off, you don't, then we could do it that way. Well, okay. You know what, though? I take that back as well, because the problem is we kind of wanted these to be slipstreamed into our... we kind of wanted these to be slipstreamed into our actual render code. So that probably actually isn't the best idea. So I think probably what we would rather do, now that I think about it, is we're going to be sampling textures in here. So you can see in here, right, that like we do a texture sampling for the reflection value. So like that's the octahedral map sampling, which we don't really care about. Here we go. So you can see us doing our array UV, like you can see the frag texture index thing, right? Maybe what we do is say if frag texture index is 0, right? Or we could say if frag index is greater than or equal to 0, and then we just pass a frag texture index of -1 for things that aren't lit or something like this. That's one way we could do debug. Now the problem with that is if we did do that, it would cause a problem where we wouldn't... It would cause a problem because we wouldn't be able to do textured things that way. So again, hard to say. Let's take a look at what that value actually is. So here's our textured vertex. And you can kind of see like, you know, how this is working. For the texture index, we can have a full 16-bit value. And it looks like actually we've got extra space too. So I suppose we could just in our vertex have a code for lighting or not. In fact, emission would be fine, right? All right, so maybe what we do is we just pass it in there, right? So we know that we've got a reserved value in there, and we actually know that there's an emission value too. I don't know that we're actually using it, so we could just try to make that work. So maybe we don't have lighting enabled. That's not a thing, right? And you know, maybe this maybe this lighting disabled value also is not really a thing either, because we can disable it now when we pass things down. So what we really need is some way for this thing to get, in addition to these other ins, like it's getting that vert texture index and all that stuff, right? What we kind of need here is a way for this to get the emission value. You know what I mean? And we just stream that in. And then the emission value would control whether you lit the vertices or not. So basically, like, the L value here, I guess we would just kind of do a lerp. I don't really know. Like that part's a little bit harder to conceptualize because we're doing like a sum here, and so I guess we probably just want something like this. We go between the like lighting that we would compute and the 111 by just doing a lerp, I guess. I mean, it's not great, but I feel like it's something for now. And when we're trying to optimize our pixel shader later, maybe then's when we would test to see, what we think about that. So I want to in here then say that the smooth value in there is just going to be like an F32 of like the emission value. And I don't need that anymore. Did I have these lined up right? So sim rates, the depth peel, light intensity, light floor, the voxels, and the diffuse. Yeah, all right, it's fine. So I guess I'm okay with that. It does mean that when we use the ZBias program, we're going to actually have to set up the attribute arrays correctly. So like in here, you can kind of see where we've got the attribute arrays when we do use program. We do like the isValid garbage here. So in there, what we're going to have to do is after texture index, we're going to have to do a similar thing. We want to do basically the same thing as the color array. So in here, we want to say like, look, if the emission array is valid, then we'll use it. And we basically want the same thing that we were doing for our color, but we want to unpack it, the unsigned bytes. We want to unpack those, right? And we want them to be 0 to 1 floats. So I don't actually know. I don't think we need to do anything other than to just say that it's not an I. So I think if we just say it's an unsigned byte, then it will unpack it to 0 to 1 automatically, because that's what it will always do with an unsigned byte. So although it's really kind of squinky and weird, and we didn't really say that, I think that's what it will do anyway, right? And so here I can also do the exact same thing, which is that I can just disable it when we're done with it. And that should be it. We now have to actually look up those values. So like right now, like that will use them if they were there, but at the moment we don't actually have any way to actually do that, like to actually put anything in there. So although we have sort of the vert stuff here, I guess this is actually should have been vert emission. Somebody's going to have to actually do something with it, right? So we'll do that in a second, but this should at least give us the ability to use it if anyone actually sets it, and no one is. All right. So if we run the code now, in theory, it should still work. Of course, I've got some GL error stuff happening here, but we just won't get any of that because no one's actually doing anything with those emission values. But, so let's take care of the GL error messages first, but oops. Message, there we go. Index out of range. Really? What do you mean? I also don't know, like, for when we do these prog values, let's take a look at where those are coming from at the moment. So this may not get cleared, would be another thing. So it may just be because we're never actually doing this. We'll see. So if I go to the ZBias program, I should probably make this actually be properly called vert emission there, because at the moment I actually wasn't doing that. So let's take a quick look and just make this a little bit better. So you can see here where we're passing emission here. I might want to call that frag emission actually. And so in here where we actually do the vertex stuff, I kind of want to do like an int f32 vert emission like so. And then I want to do a smooth out f32 frag emission. And I think I just want those to be direct assigned. So in much the same way we just do the vert UV directly there, we would do the vert emission directly. So I'd say like frag emission equals vert emission. So it's just a pass through because we don't need to change it, right? All right, so let's look at the compile errors there. So I guess I want to look at vertex errors if I can here, and fragment errors, just to see. I think I can use remedy here to make that easier, yeah. Remedy the rescue. So it looks like emission I just forgot to rename. So like down where we actually use it, I was still calling it emission instead of frag emission. So let me not do that. All right, so if we now run, let's see what we get here. Why am I not getting anything? What is happening? Something bad is happening, but I don't know what. Access violation inside the OGL NVIDIA driver. So I've told it something bad. I'm not sure what. What have I done? So my vert emission is like not right at all, but I don't know why. So in here somewhere I said, let's get the offset of the emission value of this unsigned byte. Oh, that would do it. All right. All right, so now, at least in theory, we should get a value. You can see that since I removed that, these would have to be having their emission values set, and they're currently not. What I can do here is now take a look to see if that's working at all. And so one way that I could do that is inside where we do like a push quad. So you can kind of see where we do our quad, writing here, where we've got our vertices. Here's us writing our vertices out here. We could write emission values based on whether the lighting is on or off, right? So inside here, we know whether the lighting's on and off because inside the render group it tells us. So in the render group itself, we have this value. So we should be able to, in here, handle that properly. Now, I don't actually know if we always use this. So if we look at all the places where we're doing that, you can see that there's at least 2 places. So in Handmade Renderer, there's some of this, and in Render Geometry. So here's a right quad, right? So there's a couple of people who actually do this, and we kind of need some way of making that be congruent. So if we take a look at where the geometry output stuff happens, that would probably be a good place to think about this more. I think probably most people want this emission value set to 0. So I'm just going to do that. And then only in like the debug code will we set it at the moment to anything else. So that's one place we write them, and the other 2 places we write them really, so there's very, very few places we actually look at this. but one is here and one is here. So in output quads, doesn't ever write. It's just sort of keeping that in mind. So it's really just only here. So what we should be able to do here is set this to an emission value. So all of these should be settable to like some value, right? And so now what we can do is just set this value, like our emission value can be a look to see is lighting enabled, and if it is, then it can be 0, 0, otherwise it can be FF. And that should in theory give us something we want. We'll find out. So, wait, what? Oh, we actually pass in an emission value here. I'm not going to use that at the immediate moment. But we may want to use that later, because we could actually pack that value down, actually. All right. So now, actually, we can see that this already works, which is kind of cool. So you can see that now our code that previously had lighting turned off, which was like the debug overlays, actually works now with no hack, right? And that's nice. And so now what we need to be able to do is set it to be off for certain things, like for the debug stuff there, right? And I guess the easiest way to do that would be to literally just use the packing. So when we go to, I mean, there's a couple different ways we can do it. I'm not really sure which one we want to use, because this is not really the part of the code that I really want to be working on right now. So I'm not motivated to like do like a super fancy solution. But if we take a look at how push line segment works, you can see that it just falls through to push quad here. And probably what I would assume is that in this particular case, the push quad that it's calling, we probably just want to pass a full emission value down, right? So we just say that emission was 1 there. And then when we do the actual push quad, yeah, which is here. What we want to do is pack the vert emission. So probably what we want to do is say, like, look, if group lighting enabled, if that's not on, then the emission value is 1 always, because it just is automatically going to not use the lighting. But otherwise, we should actually pack that value down. So we should have a like, we sort of want like a clamp binormal packed, but I don't know what we've got. So it's like, it's basically, the same as a BGRA pack, but we're only doing it for 1 value. So like, we want the ability to pack one of these, just one. And I don't know what we've got for that at the immediate moment, right? Like I don't actually know what's going on with that. But somewhere in here, what we want to do is say, okay, like clamp 0 to 1 emission times 255, right? Basically. So we're just packing to 255 just because that's what the graphics card can read more efficiently. Like there's no sense storing a whole float because the emission doesn't need to be that detailed. And so now in theory, like we should and do, which is great, we should be able to see our debug colors properly, right? And so you can now see like it's kind of nice and clean coming through here. All of the colors are as I asked them to be. So now it should allow me to do something with my existing code, and we'll basically be stopping here for today. I don't know how much time we have left, but probably very little. At most 15 minutes, but possibly like as little as 1 minute. I don't actually remember. But anyway, what I was trying to say was, now I should be able to do stuff like change the lighting, how bright like one of those cubes is based on whether it has leaves or not, and other things like this. So inside the grid raycast code, what I can do now is take a look and say, okay, when we actually do the leaf hit testing, so you can see us looking at the cell bounds here, right? I can look and say, you know, are these two different? So I can do something like, you know, v3 color or box color equals, you know, these two things being equal to each other, and then produce two different colors based on that, right? So then I can say, you know, I'm going to make this thing be dim cyan in the case where there isn't, and bright cyan in the case where there is. And then that way, like when we, does this, don't know why I did that. And that way I can just have a little bit better understanding of, as we're traversing through, like, did it ever test any leaves at all? And then eventually we'll draw the actual leaves themselves, but I just kind of wanted to see. And what you can sort of see there is some sort of semi-nonsensical results. So it looks to me, and I could be very wrong about that, but it looks to me like these are actually in. And maybe this was too subtle. Like maybe this should have been like this, so we can really see what the difference is, right? And that way there's like no ambiguity whatsoever whether we've hit one or not. And so when I run this now, I should see like which ones have leaves. Yeah. So, you know, this gives us, I'm going to go ahead and wind down for today, but this gives us a great place to start tomorrow. We've got our ability to draw things clearly. We now know like definitively that some weird stuff's happening with the spatial data structure because these all supposedly have leaves, which they obviously don't. Only this one should have a leaf. The rest of these should, like at least these two and that one, like, so these three right here are the only ones that could plausibly have colliders in them. These obviously don't. I mean, we're looking at them. There's clearly no colliders there. So that's great too, because that allows us to sort of give us a great place to start debugging from there. We already know what we're going to do. So we'll go to a brief Q&A. I agree that the hair is getting very cartoonish. I'm kind of thinking, let me just see if I can find it here. I thought there was a yeah, so like I feel like I could kind of start going down this route a little bit. Like I feel like I could do some Wilson cosplay pretty soon here. Okay, somebody needs to capture that Insobot comment and send it to Abner Coimbray, because 5+ hour Majora's Mask sounds like something that he would be very interested in. Performance might have changed since you removed the early out. Oh yeah, definitely. I mean, we have no idea what the performance of this routine is at all, right? We have literally no idea, because we have to get it working properly first. and then we can actually benchmark it. We have no idea what it's doing. So we'll get it working first, then we'll do another capture, and then we'll run the two different routines together to see which one performs better, right? And we can also take some vTune testing to see whether there's obvious things we can do to improve either of them, right? Looks quiet, so I guess we can just wrap it up. All right. Thank you, everybody, for joining me for another episode of Handmade Hero. It's been a pleasure coding with you, as always. If you would like to follow along with the series at home, you can always go to handmadehero.org and pre-order the game. It comes with the source code, so you can follow along with it. I will be back here tomorrow to do the next phase of debugging. I think today pretty much went exactly as I hoped it would, meaning what I said at the beginning about how visualization helps you zero in on bugs very quickly, much faster than, say, unit testing or things like that for algorithms of this kind of complexity and geometric sort of, orientation. And I think that's exactly what we saw, right? We were able to find at least 3 bugs very quickly by doing nothing other than just drawing. And so for something like lighting, where it's such a visual problem anyway, it just works really, really well. Anyway, now that you have the ability to do that, if you are following along with Source at home, you should be able to go find some more of the bugs before I do tomorrow, because I can't program until then, and you can. So you should try that if you're interested in an exercise. But I will be back here tomorrow. Hopefully I'll remember that the time is 11, not 12 tomorrow, to do the next round of debugging. Hope to see you back here for that. Until then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.